So, good morning, everyone. Today we have Mr. Jung from USC presenting for today's global seminar series. Okay, so since I have never met Mr. Jung, I will let Mr. Jung to introduce himself, and the title of his presentation is gonna be embedding functional materials within structures via hybrid vat it's a long word, photopolymerization.
Yes,
So, Mr. Jung, I will give the stage to you. Thank you.
All right. Thank you so much, Professor Tingwei. So I can't see everyone in the classroom, so I just pretend I saw you guys.
Yes.
But
yeah, sorry, we didn't set up the camera, but we are here.
Okay, awesome, great. Yeah, I can start. So hi everyone. My name is Yoon Yoon. Hopefully it's afternoon there in Taiwan, Taipei. Here it is almost 6 o'clock. So my name is Yoon Yoon. I am a PhD candidate in Department of Mechanical Engineering here at University of Southern California. So I'm working at the facility called Center for Advanced Manufacturing. If you guys remember last week's talk, we have a Neil, I think, gave a talk last week. So we are all working here and working on the advanced manufacturing. So today I'll be talking about my own personal projects and extend it to my PhD proposal, which is embedding functional materials within structures using that photopolymerization. So a little bit of introduction about myself, since we never met. So I did both of undergrads and then master's in mechanical engineering. I did both in South Korea in Sogang University. So after finishing my master program, I decided to go a PhD in USA. So I'm currently pursuing both master's degree in computer science and then also the PhD degree on mechanical engineering right now. So I wanted to pull up some connections with Taiwan. So I had this memory of visiting Kaohsiung about 6 years ago in 2017. So I was attending IEEE Transducer Conference, and then I still remember the very hot, humid weather, and then also very nice food. So my research interest was more on micro nanoscale electromechanical system, so-called MEMS and NEMS before. But now for PhD study, I'm more focusing on advanced manufacturing. My special focus is on additive manufacturing of functional materials and the optimization of the 3D printing process, and also hybrid of the existing AM process into a more advanced system. So that's brief about myself, so I think I can continue. So today's talk, there's a little delay on the screen. Okay, there you go. So yeah, today's talk will be on this sequence. So I'll basically introduce some of the basic of additive manufacturing industry because I'm mainly going to talk about that, and then some of the problem statement with the results, and then we'll conclude with conclusion. So basically I'll mainly talking about two things today. First is using a process embedded programmable structure design with hybrid printing. And then second is also a hybrid printing method to create print magnetic composites for soft actuators application. So I'll be just go back and forth between problem statement, result, and conclusion. So hopefully there is no confusion coming forward. So my topic is evolving around of this material called functional material. So functional material is nothing so fancy. It's just the term that calls any type of specifically designed material with determined function. For example, if you look at this is pretty common in nature. So if you look at octopus arm, you basically have octopus that grip on the both on the wet dry surface with very strong adhesions. Also, we have a piezoelectric material, also popular in use any sort of clock or timing device. And if you look at the fly eye, a very complex compound lens is evolving around their eye visions to create a large field of view. And if you look at the spiral silk, that has a pretty resilient stuff, but it gets very flexible. So it is often challenging for us to do this artificially, but we're still able to pull it off. For example, suction cups are manufactured using 3D printing method or soft lithography approach. And a lot of interesting research is lying on the stretchable nanoelectronics. I'm sorry, just gotta move this a little bit further up. Okay, awesome. Right, and then also people try to 3D print the spider web using synthetic polymer. So a lot of challenges actually is behind this because we actually want to print this or manufacture it in an artificial way. So people are thinking about what is the effective way of creating these functional materials artificially. So one of the popular way is manufacturing, of course. Among them we call additive manufacturing. So we call additive because it's an additive process. You basically have a 3D CAD model, and then this model will put into the slicer. We call it slicer. Basically, it is processed to have a thin layer, and then this thin layer is becoming an object using either point printing or line printing or area printing to create a 3D structure. So additive manufacturing basically refers to, it's the same terminology for 3D printing, but it basically builds up a component in layer by depositing material. So there are 7 popular additive manufacturing process. We're not going to cover all of them, and I'm just going to cover some of the AM process that I utilize for my research. So additive manufacturing is pretty dominant right now, and it's pretty, it's evolving into more into our life. For example, from robotics, electronics, metamaterial in aerospace business, and even in the food industry. So if you guys into sports, I think NBA announced like airless kind of basketball was produced by 3D printing, where inside it's just a pore structure that has the same mechanical property of like air ball. So these are very popular, and then additive manufacturing itself, revenue is taking up on the rise. So last year, the revenue on both product and the service taking up about $18 billion in general in the report. Today I will just talk about 3 different additive manufacturing process that it's directly related on my research. And then this is basically about a little bit of the introductory for those of you who is not really familiar with 3D printing additive manufacturing. So we're just going to cover 3 different processes, material jetting, extrusion, and the wet photopolymerization in those sequence. So first off is material jetting. So material jetting is pretty popular industrialized 3D printing approach. So basically they have a few or a single inkjet nozzle. So it's a solenoid valve that creates the discrete droplets. And then it works as a print head, so it dispenses a few droplets on top of substrate. And then either it could be thermally or photo cure. And then once it's cured, you can basically write another layer on top of it. So you can think of it as an inkjet printer exists, but inkjet printer with the volume. So the good thing about material jetting is that it can achieve very high resolution, and then the beauty of it is you can basically include a lot of nozzles together, and they could be high throughput. And the multiple material printing is fairly easy using this process. But the downside of this is pretty costly, the system is pretty complicated, and also there's a material limitation you can print because you only have a solenoid valve. That means you can always work with the low viscosity liquid. The second process I want to introduce is the material extrusion. This is by far the most popular 3D printing. People call it fused deposition modeling or FDM, or a lot of a different approach to it is called the direct ink writing. So it basically is it selectively dispenses materials through a nozzle and a solidifier. So once it's cured to one layer, it goes to the next layer and print. And some of printers, it comes with 2 different types of nozzle. One's print the materials, and other one's print the support material that you can print overhang structures pretty easily. So this is very cost-effective process in a way that you don't waste a lot of materials. And then you can also print a lot with the cheap material side. And then multi-material, you can fairly easily do this. And then if you are choosing with the polymer, you basically have a wide range of material you can choose. Yet you can also always print thermoplastic using this process. So mechanical property of the finalized device is not as good as engineering plastics or engineering like metal engineering material. And also the resolution of this process is solely defined by the nozzle size. So there is a limited resolution we can achieve. Second process, and then the last process I want to bring about is the vast photopolymerization. There's many terms to call this. We call it stereolithography, SLA, VPP, that's a vast photopolymerization, or resin printing, that is all this, calling the same thing. So it basically is we have a light-sensitive polymer, and then we use sort of light engines to cure this polymer. So once it's exposed to UV, the light precursor will become solidified and then become a solid pattern. So it's basically a light to write a polymer. So here there's a few more variations to this based on how they choose the optical engines. So people differentiate by the type of light engine they use. So the stereolithography is using a laser, basically a laser to print material. DLP is another popular thing. I think I myself is projecting on the screen right now using a DLP projector in the classroom. So it's basically a spatial modulator that can create a 2D pattern. LCD is also another cheap and a very cost-effective way to do resin printing these days. So what's the benefit of that photopolymerization, or I'll call in future VPP or VP process, is that it by far can achieve the highest resolution that additive manufacturing or 3D printing can achieve. And then yet they just use a light to cure polymer, so the speed is relatively faster than other processes. But the downside of it, you can guess from the term itself, is a vat photopolymerization. So you need a vat, and the vat usually can only contain one material. So usually it's confined by using one or two material, and then if you print multiple material, there's a whole lot different complexity comes into bringing or manufacturing those materials. So we just looked at three different additive manufacturing process. And then, so what's so good about additive manufacturing? So we can think about it as the value per cost. So additive manufacturing is that it always costs the same, no matter if you print one material. The cost per piece is always a constant. So if you look at the left figure, if you print a lot of parts, the CIM means the conventional printing or conventional manufacturing. The cost per piece reduces, where the additive manufacturing part stay a constant. So it's very beneficial if you only print a small volume. And the second way to look at it is if the complexity of the structure increases, that means the structure is very intricate, very hard to manufacture. So conventional manufacturing, the cost exponentially increases when the complexity increases, whereas additive manufacturing cost stays steady or let's say constant. So it's fairly beneficial if you want to print highly customized feature with a relatively small volume. So there's three values in manufacturing. So if you look at the right three axes, there's a complexity on one axis, volume on one axis, and customization on one axis. So right now 3D printing is highly customized space with a high complexity space, where it's achieving around this corner. But right now, everyone wants the best. So 3D printing itself, it wants to move toward the center, where it can be still cost effective when printing in the large volume. So AM can redefine the values and scale in manufacturing, and offers great freedom and then material efficiency and high customization space. However, each additive manufacturing process evolves around a single material that is pretty much fit to each of the process. So if you look at 4 different materials to print, let's say ceramic, metal, polymer, biomaterials here. So additive manufacturing process, I'll introduce 4, and then each of material has their own favorite way to be, let's say, printed. So for example, metal is very popular method to be printed as a powder bed fusion, whereas other methods are not very good at producing metals. Polymers are, on the other hand, is pretty popular and then adopted in many other fields. So each of these material with own properties, different properties, let's say mechanical, electrical, magnetic, optical, all different properties, but it's really hard to, and let's say if you want a tool that can bring different components into your part, you have to think about the way to bring different additive manufacturing process into one. So my research question, so what if we want to print something that's a biomaterial but encapsulated by polymer? What if we want to print something that has a metal part but also in the shape of polymer? So I was trying to think about this as a hybrid printing approach. So if we want to design a material property with the design and functionality, we might want to not just use one additive manufacturing process, but multiple processes at the same time. So there comes my schematic of research. So let's think about materials. We have ceramic, metal, polymer, biomaterial, composite, anything. And then what we want to achieve, I want to achieve, is a functionally embedded structure that has multiple functionality inside of the structure. So the thing I could achieve here is either using additive manufacturing process or 3D printing, or relatively traditional manufacturing process, including molding, moulding, or replicating. So here, if we want to do electronic structure, optical, magnetic application, I divided into two different materials that we can print, which is first is the functional materials, and then structural materials. So structural material could be a matrix of the dominant materials, where the functional materials could be embedded in the relatively small volume, but still achieve the same functionality. So here I'll be talking about two main things, using a material extrusion, material jetting to print functional material, and then the main structure will be in situ fabricated by VPP, or same term for that is a resin printing. And then in this system, integration can be done in both ways, either open feed-forward system or closed loop system. But today I will just talk about the first one, which is the open loop system. So the very first topic I want to bring about is the porosity embedded structure. So porosity embedded structure, in the easy term, is like a sponge. So it has material. It can encapsulate air inside, which means it has a small pores inside. So it's basically pretty ubiquitous in nature if you look around. So including lung cells, and then skull, bone structure, and then also the honeycomb structure. They all evolve around this porous structure. For example, the lung structure, they have a porosity because it can increase the surface area where you can interact with the gas to obtain more oxygen. The bone structure in your, let's say your skull hair, it basically protects your brain pretty well enough, but it also has a pore, so that means it can be a lightweight. Honeycomb structure, where the honey leaves, it basically exists in that pattern because it can minimize the consumed materials, whereas it can hold up pretty good strength using structure integrity. So the framework here is to bring two different material and then two different manufacturing approach to create a porosity embedded structure, and then that's the big scheme of the first topic. Yeah, so there is already existing method to do this using AM or 3D printing. So stereolithography or VPP is basically you can just print pores as is in the 3D CAD system. And then another method is basically using an SLA using a templating. So templating means you have a sacrificial droplets inside, then later these droplets will be removed from structure. More recent approach to this is a fluidic printing system. You basically have a, you basically have a two liquid junction to create an immersion of the droplets, and then this droplet will be later removed. And then more recently, we have a directly bubble writing system. So they have a coaxial nozzle, and then they can print either closed cells, open cells with the size control in the 3D bulk system. So there still remains the challenge of controlling individual pore sizes and distribution, and also controlling each cell connectivity in that manner. So in our lab, we kind of try to find out what's the way to incorporate porous structure with the 3D printing. So we came up with this idea using a relatively simple experiment. So we have liquid resin, and then this liquid resin is immiscible with water, meaning they're like oil and water does not mix together. So when we dispense water on top of liquid polymer, it basically floats up to the surface because of the light density of water. And then when it happens, we cure it with UV light. So everything is solidified, including the polymer that's surrounding the water. And then we try to apply another resin on top of it to make sure this structure can contain water even with another layer on top of it. And then we found out, as you can see on the right bottom figure, that all the water droplets are actually captured inside the polymer. So inspired by this work, we came up with this idea of 3D printing of the porous structure. So it goes from A to F process. We basically dispense a liquid, which is DI water in this case, and then we capture it using a DLP projector. So every layer is solidified, including that surrounding water. So basically this one goes down, another resin layer come up, and then we dispense another droplets and then cure it. So this goes on to print a structure where there's inside multiple water droplets are located. So once it's done, we take out the sample from the substrate and then heat it, and then the water will be evaporate. Later will be all remaining is the structure with the pores inside. So we can 3D print a porous structure, porosity embedded structure using this process. So this is a video of how it goes. You basically have a liquid precursor resin, and then on top of that, we're dispensing water droplets. And then once it's done, it will retract and then basically cure with the square box. So the system of this is relatively simple. So we basically have a customized resin printing setup, and then we had to install another XY plotter that has the solenoid valve nozzle. So the nozzle size we are using is about 130 micron size, where it can create from 50 to 500 micron size droplets. So all this controlled by a microcontroller and a PC. Then basically we write a G code to run the whole sequence. Okay. The first thing we did is to control the droplet size. So we learned that droplet size is dominantly controlled by 3 different factors, including pressure, nozzle release time, and then the frequency of the solenoid valve. So on the top figure, you basically see 4 different images with 4 different pressures to be printed. So if you basically have a higher pressure, it pushes out more water, ending up in creating a big pores inside of the resin. So on the bottom 2 figure shows varying release time. So if we have a 0.3 millisecond to 1 millisecond, we can see the droplet size increases, also with the increasing pressure. So the varying pores frequency means how often you're creating the jet stream, and then the faster it is, the bigger size of the drop that it creates. But after some point of pressure, it saturates to the size. So here we are able to create from 100 to 500 micro size in diameter. The second study we did is to figure out how closely we can put droplets together. So is there any critical distance we shouldn't put them as close? So the first top figure shows different speed, and then here different speed means different distance between 2 droplets. So if you move slowly, you basically have a shorter distance between the droplets. And what happened if this droplet size putting closer together is they ended up merging as a one bigger droplet. So for printing, this is for us, it's like a artifact. So we wanted to find out what's the critical distance between the layer we can put droplets together. So as it turns out, actually, you can see X, the pitch is design pitch distance, and the Y is the printed pitch distance. And then you can see after some point, this printed pitch distance is coming deviated from the reference point. That means droplets are started to emerging. And then if you see on the right bottom figure, if the pitch distance decreases at some point, you can see the error bars kind of getting increased with the diameter increases. That also indicating droplets are merging, becoming a one bigger droplets. So here, we learned that printing pitch of the 2 droplets should be larger than the diameter to avoid merging, and then that enforces us to print within the critical pitch distance between 2 droplets. Once we figure all that out, next we print a few samples with the 3D structure. So this is the cuboid pattern if printed in millimeter scale. The top and the bottom only difference is inside the pore size is different. So the top one is about 200 micron size droplets inside. The bottom one has a little bit bigger, 300 micron, where the top one is about 36% of porosity. Bottom one has about 44% of porosity. So using this is a bulk material can only achieve about 50% of porosity. So in that case, we want to push it further. So we have this scaffold design using both inkjet insertion and the DLP projection. We printed this scaffold already printed out, having a bigger margin of air inside, where we are able to print a scaffold structure with a 37% of the porosity achieved. So this shows the benefit of having both of the printing system at the same time where you want to achieve higher porosity. Another example we wanted to show is the graded material. Graded material is that you gradually have different modulus around the same bulk material. So here you see the cuboid pattern that has a bottom side relatively larger size droplet, and then this transition happened on the two steps where the top is having a 150 micron size diameter. So if you look at just one material cross-sectional wise, the bottom would be a little bit relatively softer, where the top portion will be relatively stiffer. So we had to validate this using a mechanical test. So here we have pore A, pore B, using different density. And then this is a mechanical compression test to calculate the elastic modulus of each material. So whenever the density is full, where there's no bubble, and then it reduces when we have about 67 gram per centimeter in square, centimeter in power of 3, that we were able to decrease in 44% in elastic modulus, where the density is down by about 40%. So we wanted to push this further to see how small of the change or how much of the change we can achieve using a single material. So here you see examples of printed sample using all different sizes. So C4 means 4 droplets into one, having about 400 micron, to C10, about 500 micron. So we are doing all the compression tests on the same samples, different samples, and then here, this is the elastic resin without any pores, having about 8 megapascal. And then all these variations are achieved the same resin, but putting in different diameter of the droplets inside. So having a larger droplet ending up in the lower elastic modulus, where the maximum size of droplet of the C10, we're able to achieve about 11.8% of the bulk modulus. Yep. I think I'm going pretty good, not too fast, hopefully. So yeah, summary of this porosity embedded structure printing is basically this hybrid additive manufacturing method by hybridizing inkjet printhead into a 3PP or a resin printing process. So we are able to control the size, location, and the density of the cavity inside of 3D structures, either in open or closed cell manners. But here I didn't show in detail, but it mostly closed cell. But we are able to achieve the open cells in the vertical direction. The current fabrication approach, we're only able to about 50%, 45% in the modulus density, but we are able to push this further using a 3D printing design. So homogeneous bulk packing can achieve about 11.8%, and then this we're further looking into design optimization tool to program material properties. So that was the one chapter I wanted to bring about using hybrid 3D printing. And then let's change the gear slightly, so introduce another way of printing metal composites. So next chapter I want to talk about is a metallic composite embedded structure. So it's slightly different, but in the big picture wise, it looks pretty similar. So there's always a big needs to 3D print polymer composites, because composites are the one that has actual functionality, including electrical or biomedical, robotics, and energy application. So electrical, what you see here is the liquid metal particles inside of the very soft elastic material, so they can stretch it out and use it as a sensor. Biomedical application means you basically have to mix some sort of resin as a binder, and then the particle as the core material. So once you print this, you have to sinter it to get rid of all the polymer, and then the ceramic grows inside to work as a ceramic particle. So robotics, for example, they have this very soft structure, and then inside their magnetic responsive structures are there to create different morphology, different actuation point among the magnetic actuations. So all of these are called polymer composites in a way that they have a mixture of two different materials. So the filler material is in the red box, and the matrix is in the yellow box. And then the difference between two is the filler is the one that carries the functionality, matrix is the housing. So what's the problem here is we want the maximum concentration to be able to achieve maximum functionality, but there's a caveat in that, because increasing filler concentration, you ended up making polymer composite extremely viscous because of the reduced Brownian motion. So here the question is, how are we gonna have the maximum functionality while having the very high concentration, while still able to deliver the structure matrix integrity as not to the point it kind of deflects the point where we reduce the functionality. So framework here is to print metals on top of polymer, and then the printing approach, we're going to use a material extrusion where the structure material is still using a resin printer, and also this is the open feed forward system. So just example of one metallic composite, I think we can think about the soft magnetic particle. So this is a soft magnetic particle. It's basically some sort of ion powder that has a ferromagneticity towards a non-uniform magnetic field. So very easily to explain, if you have a cantilever beam full of ion particle, and then you try to bend it with the magnet, so your deflection can be determined by a few factors. If you just increase the material concentration, that will make the whole cantilever beam pretty stiff, therefore minimize deflection points. But if you want to reduce the concentration, also they reduce the actuation motion. So there's a little bit of trade-off. So if you just increase the particle volume fraction, that will basically reduce the bending. Right now, how about if we can approach this in a way that if you just increase the volume fraction, therefore achieving a maximum deflection point. So the question we came up is, can we keep the soft material properties soft while maintaining the magnetic functionality with the high volume fraction? So here, I try to suggest a way to do this is where we print the viscous material that carries the functionality, which is the filler material, which is about 2000 Pascal second. And then we still print the main housing using a resin printing. So we can selectively deposit functional, here, magnetic particles within a resin matrix. So this is the process we came up with. We basically had a top-down printing process where we just print a one layer of the resin. Here it's very soft, and we have to use a secondary laser to create a surface condition extremely dry. And where there becomes a direct droplet nozzle come in and print the magnetic slurry. And then once it's done, this goes down where the resin comes in, and then this goes on and on to create a functional composites. So here we're able to print metals, carbon. This is a CNT mixture with the resin and the ceramics, and also both of the soft and the hard magnet. So this is the key idea of dispensing viscous slurries onto the substrate. So we have this kind of plunger machine that has a needle inside. So the slurry is going to come into the reservoir, and the reservoir is fully filled. We have this mechanical cam motion, so moving up and down with the spring, basically dispense and tearing out the material out. So the key idea here is to punch the material out, so we call it droplet punching, where some few factors are going to be determined by pressure, diameter, travel height, but we're going to skip that. And then the secondary phenomenon is going to happen is once it transfer the material, the plunger is going to travel back. So there we have a capillary splitting motion to determine the size. So it's either a very discrete way of printing, and it's highly contact based, and then it can deliver extremely high viscous material is basically relying on material tearing, not on surface morphology. So this is the machine setup that we had in the lab. It basically looks very complicated, but in the nutshell, it's only two parts, where the direct writing nozzle with the laser, and the secondary module, is for the resin print. So the first step is we do the resin coating, and then a secondary laser is gonna come and then secure the whole layer to creating a very dry surface to material transfer. Second step is basically droplet writing. So we have this, you can see this spring motion ups and down to basically plunge and push out the material onto the substrate. And then finally, the step 3 is to secure this with the laser, and then it goes in, and then recoat the resin to print another layer on top of this one. So here, I just print 2 more layers, and then the print is finished. Okay, so yeah, using this, we were able to print a few materials, but we actually settled down on the magnetic particle. Here we use the ion powder. So we use both natural and the synthetic ion powder based on the application. So what you see here is increase the concentration. It basically, you can see how viscous the material is going to turn into from 70 to 83%. So for this projects, we only use carbon ion powder, which is a synthetic powder, has a spherical shape, and then just a natural ion powder, which sits on the larger size. We later found out ion powder natural has a fairly non-uniform size of the slurry, so the separation happens rather quickly on the few days. So we later settled on using synthetic powder, which shows about below 5% separation after 2 weeks of usage. And then the maximum viscosity will achieve about 2,000 pascal second with the ion powder. Okay, so these were the slurry transfer on the glass. So basically the bottom line here is if you increase the distance between the plunger and the substrate, we get a minimized transfer, because the contact of the transfer, the contact happens based on the area of your surface, the area you touch the substrate. Another factor is the pressure. So it basically increases the pressure. You basically have more material coming off the plunger, and then therefore a larger droplet. So we can see the gap. If the gap increases, with the size of the droplet decreases. Where the pressure increases, the size of the droplet increases. So once we figure that out, we move on to hybrid printing, where we actually transfer slurries onto 3D printed parts. So here, a few thing we can mention is the R, which is a splitting ratio function. So that means the splitting ratio function different by different substrate. So if you see on the right graph, increasing the printing gap actually ended up in different size of the diameter, where the polymer substrate has a larger diameter, so the transfer ratio is actually a little bit larger than the glass. Punching speed also affects the printing, where the higher punching speed ended up in the smaller droplet size. Okay, oops. Yeah, and then these are the video of the magnetic slurry punched on the elastic resin we're printing. So once that's done, the laser is going to secure it, and then we're going to print another layer on top. So that's a 2 different material printing on the substrate. So look at the results here. This is basically a sandwich structure, resin, polymer, and then magnetic slurry and polymer. So cross-section of the shape looks like a very conical structure, and then this conical aspect ratio increases with the viscosity. Then you can look at the morphology of different two types of the ion powder. And then just the one sandwich layer goes on and on to create multiple layers of the structure. So here is the ion powder 80% printed on the 5 different layers. So what do we do with this? So as I said, this is soft magnetic powder, so it responds to a magnet. The magnet, which is hard magnet, that usually have a gradient of the magnetic field density. So if you approach magnet, this cantilever beam kind of attracted to it. So we were thinking it as using as a soft actuator. So here I printed a few samples here with the shorter deflection, shorter length, and then into a middle and the large cantilever suspended structure, where the longest beam has the most deflection, maximum deflection, where the shorter beam has a shorter, smaller deflection. And then this is the one fixture of the suspended structure. And then if you just
fix it on the 2 point, it becomes like a bridge structure. I think most of you learn it from solid mechanics. And then this will give a more restricted actuation motion than a one-side fixture point. So SML means the different length of the bridge, and then RS and SS means the serpentine structure. So just using simple idea to print different length, but if you incorporate this with a very flexible pattern, you can achieve about 6 times better in the deflection. So this one is to show off with the 3D printing what we can do with the magnetic particle insertion. So first idea we had is what if we use it as some sort of magnetic valve? So the idea is we have normally closed valve as like a flapper, and then we apply pressure. So normally if it's a pressure, it's gonna push the cantilever beam down, so there's no flow out. So the valve is closed. But whenever you have a magnetic influx coming in, the cantilever is gonna react and then go up. And then through this opening, the pressure is gonna go through and then have a flow. So this is, the first one is the off, and then the second is it's on with the flow. So we designed this assembly with the cover and the housing, but the valve is kind of clamped inside. And then these are printing results. So we are able to print different density of the magnetic powder inside, where it kind of responds to the magnet up and down. So where we can decide what is the best density that it can react. So these are the layout of the experiment. So you can see if the valve is open, it works at a certain point. Here we are able to achieve about 30 kilopascal. And then if the pressures become higher than that, this bending motion cannot actually overcome the pressure. It becomes closed valve again. So we think this can work as some sort of safety valve. It only works in a certain range of the pressure, and then if it goes too high, the valve shuts off itself. The secondary idea we had for this study is some sort of smart responsive gripper. So there are actually a few cases of using magnetic, like smart adhesive, like a smart gripper. It's either using surface bonding that has a surface grip with the actuator motion, or that has the surface vacuum grip with the actuator motion. So we came up with this idea about using this as a suction cup, but it can selectively choose and release a substrate. So if we have a cup that kind of pushes in and it create a negative pressure inside, so it's just like a suction cup in your bathroom, you just push it into the wall. But if you want to take up, what you do is take off the very boundary point and then apply the actuation. And then when this happens, the vacuum breaks, and then it basically loses the grip and loses the adhesion to the substrate. So here we did a few tests on different surfaces, different environment. We tested on 3 different environments, including dry surface without anything, just open air, and then the wet condition with both water and oil, to see how it reacts on the different types of surface, and then complete underwater surface. So it looks like the glass has the best with the dry surface, whereas PDMS, source of FEP film, where it has a very poor adhesion to any type of polymer, they act better in those kind of wet environments. So this is a pick and place test we did on the single gripper on the different length of the bin. And then these are the arrays of the gripper that we printed. And then this is the video. It shows to grip something, and then after some point it loses when the magnet approaches. So it lifts up. This is about 60 Newton. And then the cantilever actuated, therefore loses the grip. Yeah, so this secondary study is on hybrid additive manufacturing by incorporating direct droplet writing with that photopolymerization to insert a magnetic soft powder inside 3D printed structure. So DW, or direct writing, realized with stereolithography, where we can print extremely high viscous slurry up to 2,000 Pascal a second. We have a very highly customized space for the magnetic actuator design, where we can control the shape, location, and the density. So we're able to pull off some test study with the fluidic valve and the smart actuator. So that kind of sums up my talk and my work here. So the thing I want to produce is the tool set that can deliver functional materials with certain type of additive manufacturing approach, where we can still have a main integrity using a structure material, using another 3D printing method, or it could be one method, So I didn't explain here, it could be either open loop or closed loop where we can feed control back and then forward. So my research is actually including both of the structure, mechanics, structure, designing space for additive manufacturing, also magnetic actuation. Here I didn't mention the last one, but we are actually trying to print a tumor pattern on the human tumor cells to block and selectively choose the DNA. I think that's all I had today. So I am here in Los Angeles. I'm here at the USC. So we are kind of off-site lab facility called Center for Additive Manufacturing. So we actually have a YouTube channel that you guys go there and check out. We kind of do a fairly recent upload on the YouTube channel, and it's definitely something you want to check out. So yeah, I just want to thank to my advisor and then my research collaborator that contributes to this work. Thank you very much, and then I'll be happy to have any questions.
Thank you so much. Okay, so before the students start their questions, I do have a question about optimization for additive manufacturing. So in the past, I did a project to build shoes structures, like I don't remember the name, right? Like the layer structure inside the shoes, and they want us to design like a hollow structures, and it has to be soft enough so it's comfortable, but it should be strong enough to carry the stress. So at the time, it's really difficult for me to figure out what's the best way to formulate the optimization, because being soft and being strong basically are conflicting trade-off ideas. So how do you maintain those at the same time? So I realized the technology is there, but in the design viewpoint, sometimes could be difficult. So have you experienced research directions like that, and where you may want to design something like you need the structure to have multiple purpose, and those purposes are conflicting? What would you deal with that?
Yeah, it's very, very, very good question. I often have that sometimes. So for example, I can take from my talk today is the purpose of the printing of porous structure is to make a whole structure very soft, not to the point it loses the integrity of the structure. But the conflicting point of that is it kind of loses its functionality. If it becomes too soft, and then the point of having a porosity inside is to still maintain it. So hopefully for us, if we just go to the direction where we minimize, let's say, modulus of the structure, we can basically print a very thin structure without any bubbles inside. But we have to set a boundary to maintain. So I want the elastic modulus to be at least 10% of the existing structure. Otherwise, our method is not actually beneficial at all. So yeah, it's the kind of question I ask myself all the time. What is the beneficial compared to existing competing idea? But I try to draw the boundary as much as possible on the research side.
I see. Seems like we are all dealing with multi-objective optimization problems with multiple constraints.
Yeah, it is very true. It is very true. Yeah.
I see. Okay. Does the student has any questions? Okay.
Hello? Sorry, I have a question. I'm just curious about, and you just introduced a novel way to do the 3D printing. And I'm just curious that, is it faster than the previous method, like the material extraction? And it still need to use the support part a support structure to when he facing the hollow part.
Yes. Can you say the first question again? I think I was disconnected for a few seconds.
Is it faster than the previous method you do the 3D
Oh,
printing?
okay. Yeah. So the first question is it faster? The short answer is no. So it's slower because we are combining two different additive manufacturing process. We have to finish the first one, introduce another one, and then another one. So it's basically a slower process if you compare. For example, but if you're comparing with existing printing method to print bubble structures, we are relatively faster comparing like the ink writing. So our method is printing one layer at a time, and that the ink writing is printing lines. So in that manner, it could be a little faster. But if you just take out the components, inkjet printing, and then SLA printing, we're actually combining them and then wait until the other process finished, so it's actually slower. Yeah. And then, I think I forgot the second question, sorry.
Okay, my second question is, you still need to use the support structure when he facing the hollow part?
Yeah, so the answer is yes, we still need to use, for the second structure, for example, like the gripper, let me show you this again. Here we want to 3D print this cup shape, and then we are printing upside down. That means inside is a hollow structure. So for here, we don't use a support structure, but if the hollow structure becomes bigger, we have to use a support structure. So that's yes for the second project, but for the first one is no, because we are using a water as a support structure. So water inside work as a kind of way to sustain the material. So if the hollow structure is the droplet, then the answer is no, but if the hollow structure is something that we can define by 3D printing, then we have to use a support material.
Okay, great. Thank you so much for today's presentation.
Awesome, thank you.
So I hope we can physically meet each other really soon. Maybe our team flying to USC, or maybe your team flying to Taiwan.
Yeah, that sounds great.
It will be. Have you been to Taipei?
Oh no, I only been to Kaohsiung. So I actually wanted to go to Taipei.
In that case, I must invite you.
Yeah.
Okay, hopefully, that could happen really soon. Thank you so much. Look forward to our next meeting. Thank you.
All right. Thank you so much, Professor.
Thank you. Bye-bye.
Bye-bye.